Yes, so we'll be discussing the starting methods, right? Starting methods. Starting methods of a three-phase induction motor. Induction motor. As most of the students are aware that a three-phase induction motor is basically a self-starting motor. So if you recall, for the production of electromagnetic torque, the relative speed between the stator field and the rotor fields, or the relative speed between the two fields, has to be 0. If you remember the working principle, the stator frequencies and the rotor frequencies at starting will be the same, f. Then the speed of the stator field and the rotor field will be ns, and the relative speed between the two fields will be 0 at starting, and hence the motor has a starting torque. But very unfortunately, in case of a synchronous motor, the relative speed between the stator and the rotor fields are not 0 at starting. The stator field will be rotating at ns, whereas the rotor is excited with a DC, the rotor field is stationary, and the relative speed between these two is not 0, and hence a synchronous motor is non-self-starting motor. But whereas a three-phase induction motor is a self-starting motor. So as soon as you give a three-phase supply with the rotor circuit closed, then the motor will start rotating. So we know that it is a self-starting motor. Then why we need a starter? What is the necessity of a starter? Why we need a starter? As the name says, the starter is for starting the motor? No. The starter is not for starting the motor, as a three-phase induction motor is a self-starting motor. Then why we need a starter? Means to limit the high starting currents, the high inrush of starting currents. So when I am trying to use the term high inrush, I'll try to give a small example. You take a dam, water dam. So you know that, so we'll be collecting the water in the catchment area in the reservoir. So that is stored in the reservoir. So whenever you are trying to open the dam gates, it looks like the water is rushing. It looks like the water is coming out. So from the reservoir, and it is flowing through that dam. So that you can see the rush. It looks like a huge quantity of water is available. As soon as you're opening the gate, it is rushing. So here also, whenever you're trying to start a three-phase induction motor, the high inrush of current, high starting currents will be flowing in the windings. So because of these high starting currents, so the ohmic losses or the losses in the winding, due to that winding resistance will be more. Because of that, the temperature will increase. Because of the increase in temperature, the insulation will melt and windings will get damaged. So that is the reason, to limit such high starting currents, we need a starter. So as the name says, the starters are not for starting a three-phase induction motor. The purpose of starters is to limit the high starting currents, right? So I'll try to write a statement here. The purpose of starters for a three-phase induction motor, as the name says, is not for starting the motor, as it is a self-starting motor, or as it is a self-starting motor, but it is to limit the high starting currents. high starting currents. High starting currents. So I'll write the purpose of starters for a three-phase induction motor, as the name says, is not for starting the motor as it is a self-starting motor, but it is to limit the high starting currents, right? Done. Now we'll try to identify what is the reason for high starting currents. Why the motor will draw high starting current? What is the root cause for that? So I'll be taking a simple rotor circuit, rotor equivalent circuit. If you remember the rotor equivalent circuit during running conditions, if I talk about running conditions, or when it is operating at a slip of S, So this is R2, this is J X2 naught, and this is R2 into 1 by S minus 1. So this is the rotor equivalent circuit during running condition. So this is the rotor voltage and this is the rotor current. This is during running conditions, right? So numerically, if I take any values, resistance, let us take some resistance, R2 is equal to 0.12 ohms and X2 naught, the rotor leakage reactance is say 0.85 ohms. Let us take. So generally for any induction motors, the rotor resistance and the leakage reactance will be very less. The reason is, if the resistance is more, then the losses in the rotor windings will be more than whatever the power that is coming from stator to rotor is mostly wasted in the rotor circuit. As the resistance is more, less amount of power is converted into mechanical, and hence the efficiency of the motor will be very less. So if the resistance is more, the efficiency will be less. Because of this more losses, the machine will be heating up, and hence the insulation will start melting up, and hence the life of the motor is going to be reduced. So that is the reason while we are designing any induction motor, we never ever design the rotor windings with high resistances. So the resistances will be always as small as possible. Why? Because wherever we use windings, wherever we use conductors, it is only to carry the current. So along the current carrying path, there should not be any resistance. If there is any resistance, so there will be some loss in that conducting path. So only the conductors are only for carrying the power. Along the path, there should not be any resistance, so that there is a loss in that path. So always we design the rotor windings with low resistances, right? So the resistance will be always less. The other one is the leakage reactance. The leakage reactance is also very less. It is designed or it is made very small. Why? Because if the reactance is more, then the rotor circuit will have high inductive characteristics, high inductive nature. Because of that high inductive nature, the rotor power factors will be less. If the rotor power factors are less, the active power drawn by the rotor will be less, and the torque which depends on that will be less. So that's the reason we never ever design the rotor windings, or we never ever construct the rotor windings with high reactances. So on a bottom line, I can say that for any induction motor, the resistance will be less and the leakage reactance will be less. Less resistance will have longer life, good efficiency. Less leakages will have less inductive nature, good power factors, and the torques will be high. So for that more reason, the resistance and the leakage reactance of the rotor windings will be always very small. So finally, this is the rotor equivalent circuit, right? Done. Now let me draw at starting. If I draw at starting, NR is equal to 0. When NR is equal to 0, S will be 1. When S is equal to 1, R2 into 1 by S minus 1 will be 0. If I am trying to draw the same circuit here at starting, you can see this resistance will be there, this reactance will be there, and this load resistance will act as dead short circuit. You can see this is acting as dead short circuit. So this is E2 naught. So this is I2 start. this is R2, this is J, X2 naught, X2 naught, right? This is the rotor equivalent circuit at starting. This is during running condition, this is at starting. Now if I write the equation for the starting current, so the starting current, rotor current is equal to E2 naught by square root of R2 plus 0 square plus X2 naught whole square. And the rotor losses I2 start square into R2, and the stator current at starting, if I neglect the no load current, K into I2 start, and the stator ohmic losses I1 square start into R1. Now you can see at starting which branch is not available in the rotor circuit, the load resistance. You can see which is the load resistance here, this one. This load resistance is not there in the rotor circuit at starting. Why the load resistance is not there in the rotor circuit at starting? As at starting NR is equal to 0, slip will be 1. When slip is 1, R2 into 1 by S minus 1 will be 0. So it is acting as a dead short circuit. The load impedance R2 into 1 by S minus 1 is acting as a dead short circuit. As it is acting as a dead short circuit, the value is 0. Then as I told you that for any induction motor, R2 value will be less and X2 naught value will be less. As the resistance and the reactance are less, the overall rotor impedance will be less. When the overall rotor impedance is less, the rotor currents will be very high. So generally the range will be 5 to 8 times the full load current. 5 to 8 times the full load current. Such high currents will flow in the rotor windings, not motor, first rotor winding. So because of such high currents, the rotor ohmic losses will be more. In order to supply more currents into the rotor, the stator also draws more current. Why? Because this current is high, so this current is also high. Then these losses are also high. So losses in both the windings will be high, the temperatures will be high, the insulation will melt and windings will get damaged. So you can see who is the main culprit as of now means the load impedance. Why the load impedance is not there in the rotor circuit during starting? Why it is not there at starting? S is equal to 1. Why? NR is equal to 0, S is equal to 1, load impedance R2 into 1 by S minus 1 is 0, and hence it is acting as a dead short circuit, the value is becoming 0. As the rotor impedance is less, why? Because R2 will be less, X2 naught will be less. As I told you that the overall rotor impedance will be less, the rotor currents will be high, the stator currents will be high, losses in both the windings will be high, the temperatures will increase, they start melting up the insulation coating which is coated around the conductor, so that insulation will start melting, and conductor may get short and windings will get damaged. So in order to protect the motor winding segments to such high currents, we need a starter. So this is something like with respect to equation I can say. Now with respect to without equation, let us say it is a 6-pole motor, let us assume, excited with a 50 hertz supply. Then what is the synchronous speed? Synchronous speed is nothing but 1000 RPM. Then at starting, what is the rotor speed? Rotor speed will be 0. Then what is the relative speed between these two? Relative speed is ns minus nr, which is nothing but 1000 RPM. That means the relative speed between the stator field and the rotor conductors is 1000 RPM. Stator field is rotating with 1000, the rotor conductors are 0. So the relative speed is ns minus 0, it is ns. So the relative speed is more large, flux cutting the rotor conductors will be more, EMF induced in the rotor conductors will be more, the magnitude will be more. As the EMF is more, the rotor currents will be more, the stator currents will be more, the losses in both the windings will be more, the temperatures will be high and windings will get damage. So One is the equation based analysis, whereas the other one is without equation. What is that equation? At starting NR is equal to 0, slip is equal to 1, then the load impedance is 0. Overall rotor impedance is less, the rotor current is more, stator current will be more, ohmic losses will be high, temperatures will increase, the windings will get damaged. In other way, at starting as the rotor speed is 0, the relative speed is maximum. Flux cuttings will be maximum, EMF induced in the rotor conductors will be maximum, rotor currents will be maximum, stator currents will be maximum, the temperatures will be high, the windings will get damaged. So this is without equation. So I hope you understood why the motor will draw high currents, because the relative speed is high, or in other way the load impedance is not there in the rotor circuit, right? So with respect to this, it is clear. Then how in running condition the motor will draw normal currents? Why the currents will not be more during running conditions? Let us assume the motor is operating at 4% slip. Let us assume the motor is operating at 4% slip. When the motor is operating at 4% slip, this load resistance R2 into 1 by S minus 1. So you can cross check, I'll substitute the values. 1 by 0.04 minus 1. So it is 2.8 ohm. Right, if you check, I don't know, you can check. Then if I try to write the equation for the rotor current, I2 is equal to E2 naught by square root of R2 plus R2 into 1 by S minus 1 whole square plus x2 naught whole square. So which fellow is present in the rotor circuit during running condition? You can see the load impedance is present in the rotor circuit during running condition. So even though this R2 is less and x2 naught is less, so numerically you can see R2 is 0.12 and this is 0.85. Even though the values are less, this load impedance is very high, nearly 2.88 roughly numerically. So because of this high load impedance, the overall rotor impedance will be more. As the overall rotor impedance is more, the rotor current will be less, the stator currents will be less, the losses in the windings will be less, the temperatures will be normal, and the windings will be safe. So who is going to protect, in other way safeguarding the windings during running condition means the load impedance? That fellow is not there in the rotor circuit during starting. That fellow went for tea somewhere. So it is something like this. Really he will not go for chai. Okay. So please understand that. So that fellow is not there in the rotor circuit at starting. But the same fellow, who is that? R2 into 1 by S minus 1 is there in the rotor circuit during running condition. Because of that, it is increasing the rotor impedance and decreasing the rotor current, stator current, losses in both the windings, and the temperatures will be normal and the windings will be safe. So I hope you understood the difference between the starting and the running. The equations are same, but only one branch is not there in the rotor circuit during starting. Which branch? R2 into 1 by S minus 1. That branch is acting as a dead short circuit. But during running condition, that value is building up. As the value is building up, the rotor impedance is falling. The rotor impedance will be increasing. The rotor currents will be falling. Rotor losses will be falling. The temperatures will be, the losses will be less, the temperatures will not increase, and hence the windings will be safe. So who is going to protect means, in other way, why the currents are not high during running means because of the load impedance. So without equations I can say the rotor is rotating with a speed of 1440 rpm. Say, then what is the relative speed now? The relative speed is ns minus nr. So it is 1500 minus 1440. So it is nothing but 60 rpm. 60 rpm. You can see the relative speed is 60 rpm. You can see at starting the relative speed was 1500 rpm, but during running condition the relative speed is very, very less. As the relative speed is less, the flux cutting the rotor conductors will be less, EMFs will be less, currents will be less, losses will be less, windings will be saved. So you can just explain. So at starting, the relative speed is ns, flux cuttings will be maximum, EMFs will be maximum, currents will be maximum, ohmic losses will be maximum, temperatures will be very high, insulation will melt and windings will get damaged. But during running condition, the relative speed is very less. Minimum, starting maximum, during running minimum EMF, minimum current, minimum losses, less temperature, windings will be safe. In other way, during starting, the load impedance is not there. R2 into 1 by S minus 1 is not there. As a result, the rotor impedance is very, very less. The rotor currents will be very high. The ohmic losses will be very high. The temperatures will be very high and windings are prone to damage. But during running condition, the load impedance is present in the rotor circuit, which is increasing the rotor impedance, which is reducing the rotor current, and hence the windings will be safe. Right? I hope you understood why the starting currents are high, why the running currents are normal in case of a induction motor. Now the question comes, how to control such high starting currents. Now if I look into this starting current equation, what is that starting current equation? So starting current is equal to E2 naught by square root of R2 square plus X2 naught square. So what are the parameters by which I can control the starting current? Means one is E2 naught, the second one is R2, third one is X2 naught. So these are the only parameters which are available to control the rotor current, thereby the stator current, thereby the windings temperatures. So if you are going to control the rotor current, the stator current will be in limit, temperatures will be safe. So what are the parameters we are having in the rotor current equation to control the rotor current? One is E2 naught, the rotor voltage at standstill, the rotor resistance and the leakage reactance, right? So if you recall, in case of a slip ring induction motor, we have the provision of adding external resistance in the rotor circuit. The reason is, if you are adding an external resistance in the rotor circuit, it is to improve the starting torque. I think you are aware, or otherwise you can see in the video classes. So if you are adding a resistance, so you are making the rotor circuit highly resistive during starting. When you are making the rotor circuit highly resistive, the rotor power factors will be very high. If the rotor power factors are very high, then the active power drawn by the rotor will be more. As active power drawn by the rotor is more, then the torque which depends on that will be more. So like that, we are increasing the starting torque by adding some external resistance in case of a slip ring for driving heavy loads. In other way, if you are adding high resistance, the angle between the stator field and the rotor field, I mean to the resultant field and the rotor field axis, you are trying to make nearly 90 degrees. When you are trying to make 90 degrees, those attractive and repulsive forces between the stator and the rotor poles will be maximum. The developed torque will be maximum. So as soon as you are making the circuit highly resistive, the angle between the two field axes you are making 90 and you are increasing the motor torque. Right? So I think in case of slip ring, you are going to study or you might have learned, so we can improve the starting torque by adding some external resistance, right? So whatever the resistance you are adding in the slip ring to improve the starting torque, it is not only increasing the starting torque, even it can limit or control the starting currents also. Why? Because whenever you are adding some external resistance, the rotor resistance, the total rotor circuit resistance, you are increasing. When you are increasing the rotor circuit resistance, the rotor impedance at starting is increased. When you are increasing the rotor impedance, the rotor currents will be less, the stator currents will be less, the ohmic losses will be less, the temperatures will be less and windings will be safe. Like that, in case of a slip ring induction motor, we are going to limit, control the currents with that external resistance. But here point to be noted is we are not using that resistance for controlling the current. That resistance is for improving the starting torque. It is playing a dual role, improving the starting torque and also limiting the high starting current. So for that, so in case of a slip ring induction motor, we are not using any external starters to control such high starting currents. But that possibility or that feasibility is not there in case of a cage rotor. Why? In case of a cage rotor, the rotor circuit is shorted. The rotor bars are permanently shorted. So in case of a cage rotor, it is not possible. In case of a cage rotor, the rotor bars are shorted permanently. So we don't have any provision. To add resistance or to add anything. So as the rotor circuit is permanently shorted, right? So we don't have any provision. So for that, so in case of a rotor circuit, we don't have anything to do. Then how to control such high currents in case of a cage rotor? So in case of a cage rotor, the only one parameter by which I can control the current is E2 naught. And if you remember, this E2 naught is directly proportional to E1 by A, and E1 is directly proportional to V1. So V1 is nothing but the supply voltage and I1 is directly proportional to V. I mean to say that the rotor current at starting is approximately proportional to the supply voltage. So if you want to reduce the starting current, the only one mechanism in case of a cage motor, is to start the motor with reduced voltages. So to start the motor with reduced voltages, right? So can I say like this, in case of squirrel cage induction motors, the starting current is controlled or limited by starting the motor with reduced voltage. Let me read. In case of squirrel cage induction motor, the starting current is limited or controlled by starting the motor with reduced voltage, right? But what is the problem we are having with starting the motor with reduced voltage? If you look at here, the starting torque is directly proportional to voltage square. So whenever you are trying to start the motor with reduced voltage, what happened to the starting torque? The starting torque will decrease. That means we need to sacrifice some of the starting torque. So in order to limit the high starting currents, so we need to sacrifice some of the starting torque. But I think you people are aware that a squirrel cage induction motor always have poor starting torques. Why? The rotor circuit is highly inductive at starting, as our rotor frequencies are equal to the supply frequency. The rotor power factors will be very poor. Then the active power drawn by the rotor will be less, and hence the starting torques will be less. But in spite of knowing that, we are going to start the motor with reduced voltage. So this will decrease the starting torque still further. Does it affect the performance? Generally, no. The reason is we are using a cage type induction motors for driving a rising loads. That means the starting torque requirements to drive that loads will be very less. So even if you are trying to reduce the voltage, the starting torque will reduce, but still it will drive the load. But you should not keep the voltage always low always. So once the motor starts rotating, you need to increase the voltage. Why? Because once the motor starts rotating, there is no need to keep the voltage low. Why? Because once the motor starts rotating, the relative speed starts decreasing. When the relative speed starts decreasing, flux cuttings will start decreasing, EMF will decrease, current will decrease, then the losses will decrease. So there is no need to keep the voltage low. Or once the motor starts rotating, the speed value will increase, the slip value will decrease, then the load impedance will start increasing. Obviously the rotor currents will start decreasing. So here the point to be noted, the bottom line is we start the motor only with low voltages during starting, but once the motor starts rotating, we try to increase the voltage and we try to operate the motor with rated voltage. Right? So finally this is a consolidated statement. What is it? Can I tell like this? In case of a cage rotor, we are going to start the motor with reduced voltage to limit or to control the high starting currents. But we need to sacrifice some of the starting torque, right? So as we need to sacrifice some of the starting torque, does it affect the performance? Generally, no. Why? Because we are using this cage type induction motor for driving the load whose load torque requirements will increase with the speed. So at starting, the load value will be very less. Even if you are decreasing the voltage, this torque will reduce, but still it will drive the load. But once the motor starts rotating, we'll try to increase the voltage and operate the motor with a rated voltage, right? So this is something about starting methods. Now, how to reduce the voltage? Why? Because as I told you that we need to start the motor with reduced voltage. Then how to start how to reduce the voltage? So for that we are having different types of starters. Before to that we need to discuss some relations. What are those relations means? If you remember the electromagnetic torque equation, electromagnetic torque is equal to K into I2 square into R2 by S. If I am customizing for starting, let TEM is equal to T start and I2 is equal to I start and S is equal to 1. Similarly, if I write T start is equal to K into I2 square into R2 by 1. Similarly, at full load, TEM, if I call it as TFL, then S is equal to SFL and I2 is equal to IFL. Then what will be the full load torque now? Full load torque is equal to K into, so here small correction, by SFL. Then if I define the ratio of these two, so T start by TFL is equal to I start by IFL whole square into SFL. So this is one equation which we need in all starting methods, right, to find out the various starters equation. So this is one equation, right? The other one is, I think you are aware of the motor equivalent circuit. So it is R01, this is X01, and as I told you that at starting this load resistance will act as a short, right? So let us assume if I am applying a phase voltage of V rated, so let it be V here. So what is the other equation? ISC. So I'll write ISC is equal to V by R01 plus J X01. So ISC is equal to V by Z01. So what is the name given to this ISC means it is the current the motor windings will draw or carry at starting when you are going to start the motor with rated voltage. So this is a very, very important definition. See, short circuit current. So please remember in all starting methods, this definition is very, very important. What is that? ISC means it is a short circuit current. So what is the meaning of short circuit means? When the load impedance is 0. When this load impedance will be 0 means when NR is equal to 0, S is equal to 1, then this load impedance will be 0. So I can say ISC is nothing but the current when the windings are carrying, when the rotor is stationary. When that rotor will be stationary, when NR is equal to 0 or slip is equal to 1. So ISC is the current that would flow in the motor windings at starting when you are applying a rated voltage. When you are applying a rated voltage. Magnitude wise, this will be 5 to 8 times the full load current. 5 to 8 times the full load current. If such high current flows in the motor windings, obviously what happened to the motor windings? The windings will get damaged. So I'll try to give a statement here. Please go through this. ISC, it is the current that would flow in the motor windings at starting with rated voltage. It is approximately 5 to 8 times the full load current, and if such high current flows ohmic losses will be more or copper losses will be more, temperature will be high, insulation will melt, and windings will be damaged. Right. So it is the current that would flow in the motor winding at starting with rated voltage. It is approximately 5 to 8 times the full load current, and if such high current flows, copper losses will be high, temperatures will be high, insulation will melt, windings will get damaged. So for that reason, we need a starter, right? So finally, can I consolidate like this, mixing up all the definition discussions what we had. So the purpose of starters for a 3-phase induction motor, as the name says, is not for starting the motor, as a 3-phase induction motor is a self-starting motor. Then why we need a starter means to limit or control the high inrush of currents. Why the currents will be high during starting means as the relative speed between the field and the rotor conductors is ns maximum, flux cuttings will be maximum, EMF will be maximum, currents will be maximum, the losses will be maximum, the temperatures will be very high and windings will get damaged. So in order to protect the motor winding against to such high currents, we need a starter, right? So how we are going to control such high starting currents? In case of a cage rotor, so we are going to start the motor with reduced voltages, but whereas in case of slip ring, as we have the provision of adding external resistance, so which is used for high starting torque, that resistance will add and decrease the high starting currents. But what is the main problem in case of cage motor we are having means, as you are going to start the motor with reduced voltage, we need to sacrifice some of the starting torque, right? But once the motor starts picking up, we increase the voltage and we can improve the torque of the motor also, right? And we have seen some equation which we need to explain all the starting methods, right? And we have find out some equations, right? And I have defined very important current. What is that? ISC. It is the current that would flow in the motor winding at starting when you are applying a rated voltage, whose magnitude will be 5 to 8 times the full load current. Now let us see the types of starters. Types of starters. So first I'll try to classify the starters as you have learned. Types of starters. One is a direct online. It is very much familiar with the name DOL starters. Second one is variable reactors or resistor starters. Third one is auto transformer starters. Fourth one is star delta starters. In this, the first one is the full voltage starting. The other are reduced voltage starting. So we'll see this in detail in our video lectures, right? So I hope you understood the necessity of starters, right? Done.